So now that we've covered both electrostatics and magnetostatics, I believe it's time to introduce time-varying fields and Maxwell's equations for time-varying fields. Now I'm going to write down Maxwell's equations and their names. We have covered most of these in our previous videos without realizing that, but there is one, which is Faraday's law, which is specific to time-varying fields. So let me write that for you. So now that I've written Maxwell's equations down in both differential and integral form, we can better visualize what we mean by Maxwell's equations. We have gone over Gauss's law in a previous video, and we have gone over Ampere's law, and the one law that doesn't really have a name. It's considered Gauss's law for magnetostatics, but I just left it blank so as to not confuse the two. It just states that there is no such thing as charge in terms of magnetic field. So the only law that we're missing to cover is Faraday's law, and it's one that is pretty tricky to visualize and to understand, so I'm going to be going in depth on Faraday's law in this video, so let's focus on that. So now about Faraday's law, it will talk about induction, basically the creation of current based on a varying magnetic field's flux that links the surface area of the cable in time. So it might be a little difficult to understand, but let me explain. If we had a coil wound up in a loop, so I've drawn here a coil connected to a voltage source. If the voltage source is DC current, that means that this magnetic field, which I have drawn in blue, will stay constant. However, if we added an AC source, that would mean that this magnetic field will vary. And so Faraday's law basically states that with this principle, we can also create a current through a varying magnetic flux. So as you can see in the formula, two things that are changing according to time will be the magnetic flux and the surface. So what that means is that you can create a voltage through this kind of changing of magnetic field, or you can change it by moving the coils. Let me write that down so that it might be easier to understand. Time-varying magnetic field and the stationary loop, which would be considered a transformer EMF. EMF stands for electromotive force. And then the other two cases that could create a current from a varying magnetic field or from a moving loop is a moving loop in a static field. So the area, according to the magnetic flux, changes, which will create an electrical current. Or the other option is a moving loop, sorry, let me correct this writing here, and a time-varying magnetic field. So these are the three scenarios that we will be looking into and that we will cover later on, and that you should probably be aware of and always look out for. And finally, I've also written down a magnetic flux equation so that we know when it is changing. So B is going to be magnetic flux density. It makes sense that the magnetic flux will just be the magnetic flux density integrated across the area. So again, if the area changes, then the magnetic flux will change because the integral will have different bounds. So that's why all of these three scenarios will create a current. So I think that's it on Faraday's law. We will go over some numerical examples later on, so thank you, and I hope this was helpful.